Picture this, a pendulum, swinging back and forth. Or maybe a whole galaxy turning slowly out there in space. Or even something tiny like a photon splitting perfectly in two. What's the invisible rule keeping things in check? Ensuring that even with all this movement, something fundamental stays the same. We kind of feel this as conservation, right? It seems to be everywhere. But today, we're going deeper. We're looking at the law behind the laws. You could almost call it the contract reality signs with itself. And the amazing person who figured this out, Emmy Noether. Back in 1918, with giants like Hilbert and Einstein around, she basically detonated modern physics quietly. So our mission today, diving into these sources, is to really unpack Noether's incredible insight, this idea that whenever motion looks the same under some change, something measurable has to stay constant. We'll explore how she tied together all these different physical laws, showing they're really just about symmetry. And we'll use this cool lens called motion theory to help make it maybe a bit more tangible.
It's really something, isn't it? Noether didn't just list conserved things. She showed why they're conserved. And motion theory, yeah, it helps visualize this. Think of phase as like a fundamental tick-tock for any motion. And the phase budget is just the total count of those ticks. When physics has a symmetry, it means the basic rhythm doesn't change. And if the rhythm's the same, the phase budget has to balance. That's conservation right there.
Okay, so her first theorem, Noether I. This connects symmetry, the rules staying the same with something staying constant. A deep link between sameness and, well, persistence.
Exactly. It's almost like nature rewards indifference. If the rules don't care about a change you make, then something measurable has to stay put. In motion theory terms, if the rhythm of the universe's operations is unchanged by a shift, the overall phase budget accounting has to stay balanced.
That's a neat way to think about it. Okay, let's make it real. What if the laws of physics don't care when I do my experiment? Today, tomorrow, same rules. What does that give us? Energy.
That's time translation invariance, spot on. And yes, it leads straight to energy conservation. If the universe's phase rules, its fundamental operating instructions don't depend on when a motion happens, then the total beat power, which is just MT language for energy, stays the same.
Like that isolated pendulum.
Exactly. Its energy is conserved.
Right.
But add friction.
Then it slows down.
Right, because friction does care about time, in a way. It's an external interaction. It's like friction is stealing from the beat budget. So the symmetry is broken for that specific pendulum loop, and its energy isn't conserved anymore. It goes somewhere else, of course, like heat.
Interesting. So it's a direct consequence. If the rules did change with time, energy wouldn't be conserved.
Precisely. If the fundamental constants weren't, well, constant, then all bets are off for energy conservation as we know it. But they seem to be.
Okay, next one. What if I slide my whole setup sideways? If the physics doesn't change just because I moved it, what's conserved then?
That's space translation invariance. Leads to momentum conservation. If moving the whole experiment doesn't change the rules for how motion works, then the phase gradient in space, that's momentum in MT terms, is conserved.
Like recoil. You fire a gun, the bullet goes forward, the gun kicks back.
Perfect example. The total momentum remains zero, assuming it started at zero. The universe keeps its spatial phase ledger balanced.
Makes sense. And rotation. If I can spin my experiment around and the physics stays the same.
Rotational invariance, and that gives you angular momentum conservation. If the rules don't have a preferred direction, then the azimuthal phase twist, which covers both orbital angular momentum, like a planet orbiting, and intrinsic spin, like an electron spin, stays constant.
And you see that everywhere, right? From ice skaters pulling their arms in.
To spin faster? Exactly. All the way down to quantum stuff, like when a single photon splits. The total twist or angular momentum is conserved between the resulting photons.
Okay, one more from this first theorem. What about shifting the phase of a quantum field everywhere at once, if that doesn't change anything physically?
Right, that's global phase invariance. Usually we talk about U1 symmetry here. That gives us electric charge conservation. If you can multiply a quantum field by a constant phase factor, just spin its internal clock hand, and the overall physics, the action or total phase budget stays the same. It means the underlying structure, the substrate, sort of locks in a current. Electric charge can't just disappear or appear from nowhere in an isolated system. It's conserved.
Wow. So these huge laws, energy, momentum, angular momentum, charge conservation, they aren't separate rules handed down. They all come from the same basic idea about symmetry.
Exactly. That's the power of it. They're all just different ways of saying the same thing. The motions phase accounting doesn't change when the symmetry holds. It's a massive simplification. It tells us something really deep about how the universe is structured.
Okay, so Noether I handles these, let's say, more straightforward symmetries. But physics gets more complex, right? Like in electromagnetism or general relativity, where things change from point to point. How does Noether handle those kinds of symmetries?
That's a great question, and it leads us to Noether to the second. This tackles local symmetries, also known as gauge symmetries. These are often described as redundancies in our descriptions, but they're much more than that. They're like deep instructions about what counts as real physical change. They actually shape the fundamental forces.
Can you give an example? How does that work for, say, electricity and magnetism?
Sure, electromagnetism has a local U1 gauge symmetry. This means you can change the phase of the electron field, for instance, differently at every single point in space and time.
Without changing the actual physics you observe, like the forces.
Precisely. And this freedom, this local symmetry, isn't just a quirk. It demands the existence of the electromagnetic field, the photon, and leads directly to things like Gauss's law and the conservation of electric current locally. It means the potentials, A and phi, aren't just mathematical tricks. They're essential to enforce this symmetry. They ensure that only gauge-invariant things are physically real. In motion theory language, we'd say this local freedom to read time loops locally forces compatibility identities to keep the overall phase beat coherent across spacetime.
Okay, and what about general relativity? That's about gravity and curved spacetime. What's the local symmetry there?
That's diffeomorphism invariance. Basically, the freedom to relabel the coordinates of spacetime points arbitrarily. Physics shouldn't depend on the labels we use.
He's pretty fundamental.
It is. And this local symmetry leads to something called the Bianchi identities. These are the mathematical expression of energy momentum conservation in curved spacetime. It's subtle, though. It means energy momentum conservation acts as a covariant constraint. You don't have a simple single number for total energy in GR like you do in flat space because the geometry itself is dynamic. Physics depends on the relationships between points, the relative phase beats, not some absolute background grid. Gravity, in this sense, is like a sinc gradient, ensuring these local relationships obey the constraints imposed by the symmetry.
It really sounds like Noether's theorems are just everywhere, underpinning almost everything we test in the lab, not just abstract math.
Absolutely. You can't really do physics without implicitly relying on Noethers. The core idea holds firm. If a symmetry isn't broken, the associated current is conserved. Its flow can't just stop for no reason. Think about Maxwell's equations for electromagnetism. The time and space shift symmetries give you energy and momentum flow. The U1 symmetry gives charge conservation.
And an antenna broadcasting radio waves.
That's just a controlled export of energy and momentum current, allowed because the underlying symmetries permit it. You're shaking charges in a way that respects the rules but radiates the conserved quantities outwards.
And at the quantum scale, you mentioned photons.
Right. Single photon OAM conservation. The rotational symmetry of the creation or splitting process dictates that the total azimuthal phase charge, the angular momentum, adds up before and after. Or consider the Casimir effect, the force between two closed plates in a vacuum.
Yeah, that's a weird one.
Well, the translational symmetry parallel to the plates is preserved, but it's broken perpendicular to them by the boundaries. This dictates which vacuum fluctuation modes survive and contribute. The force is like a pressure from these edited modes, a consequence of how the boundaries interact with the underlying symmetries and conservation laws. And relativity, as we said, the Bianchi identities stemming from diffeomorphism and invariance, constrain how energy and momentum interact with curvature. Gravity itself has to respect these rules.
And experiments back this up, like really precisely.
Oh, incredibly so. Particle colliders track energy and momentum often to parts per billion. If energy seems missing, physicists don't assume conservation is wrong. They look for invisible particles, like neutrinos, that carried it away. We see angular momentum conserved from atomic transitions, releasing photons with specific spin, to those single-photon OAM experiments, even in sound waves, phonons. Charge conservation. It's one of the most precisely tested laws. People have looked for protons decaying, which would violate charge and baryon number conservation, and haven't seen it. The lower limit on the proton lifetime is staggeringly huge, like 10 to the power of 34 years.
Wow.
And those gauge constraints from local symmetries, they show up as things called ward identities in quantum field theory. If your theory violates them, your calculations give nonsense, like probabilities greater than 100%. They're absolutely essential for consistency.
Okay, but what happens when symmetries aren't perfect? When they do break, does the whole framework fall apart?
Not at all. That's actually where things get really interesting, and where new physics often shows up. Noether's framework is crucial for understanding how symmetries break and what the consequences are.
So how can they break?
Well, there are a few ways. One is through quantum effects creating what we call anomalies. A symmetry that holds perfectly in the classical theory might be broken by quantum fluctuations.
Like the chiral anomaly.
Exactly. But it's not that the conservation is just gone. The universe kind of rebudgets itself. From the motion theory view, the phase current that seems lost from one sector often shows up in another. The total accounting still works, but the flow gets rerouted between different types of currents.
So conserved overall, but maybe transformed.
Sort of, yes. Then there's explicit breaking. This is more obvious. Like friction we mentioned earlier, or pushing something with an external force, or putting particles on a fixed crystal lattice. The symmetry is clearly broken by an external factor or a fixed structure. Motion theory just sees this as adding a source or a sink to the phase budget. The conserved quantity changes precisely because you're actively adding or removing it. No mystery there.
Okay, that makes sense. But what about something like a magnet? Below a certain temperature, it just picks a direction, north and south. The underlying laws don't prefer a direction, but the magnet does.
That's spontaneous symmetry breaking. A classic example. The fundamental laws are rotationally symmetric, but the lowest energy state, the ground state, is not. The system chooses a direction. Other examples are superconductors picking a specific quantum phase, or maybe even time crystals, which spontaneously break discrete time translation symmetry.
So the system itself breaks the symmetry.
The state of the system does, yes, even though the underlying laws respect it. And Noether's ideas still apply beautifully here. When a continuous symmetry is spontaneously broken, you get massless particles or modes called Nambu Goldstone bosons. Motion theory describes these as low-cost resync motions, or ripples. They represent the easy ways the system can fluctuate around its chosen symmetry-broken state, essentially exploring the other equivalent states it could have chosen.
This is amazing. So understanding symmetries, even when they break, isn't just about fundamental physics. It sounds like it gives us tools to build things, to engineer systems.
Precisely. That's the real power here, especially combining Noether with this motion theory perspective. We can design conservation-aware devices. We can build structures that deliberately preserve certain symmetries to protect a quantity or selectively break others to manipulate currents. Well, think about photonic crystals or phononic crystals material structured on the nanoscale. You could design them so that, say, orbital angular momentum, OAM, of light or sound is conserved as it passes through, but linear momentum gets reflected or redirected. This allows you to build things like on-chip OAM routers or sorters, which could be huge for quantum computing or communications using the twist of light.
So you're using the symmetry rules to control the flow.
Exactly. Or we can do what's called gauge programming with metamaterials. These are artificial materials engineered to have specific electromagnetic responses. We can create synthetic gauge fields, things that act like magnetic fields for neutral particles, for instance, by using geometric phase effects like Berry curvature. This lets us steer currents of light or even atoms without applying actual forces, just by manipulating the effective phase landscape.
Like topological insulators.
That's a prime example. They use these ideas to create edge states where current flows without scattering, protected by the underlying topological symmetry. It's incredibly robust. And one more. Floquet engineering. You drive a system periodically, like hitting it repeatedly with a laser pulse. This breaks continuous time translation symmetry, but can create a discrete time symmetry. By doing this, you can effectively trade time symmetry for creating new, stable quasi-energy states. It's like controlled rebudgeting of the systems phase, allowing you to engineer properties that static systems just don't have.
This really turns things on their head. It's not just observing nature's laws, but using the deepest rules, the symmetry rules, to design new functionalities.
It absolutely does. Emmy Noether, you could say, gave physics its conscience. A kind of fundamental integrity check. You simply can't create momentum out of nothing if space looks the same everywhere. You can't destroy charge if the universe doesn't care about a global phase shift. You can't cheat energy conservation without explicitly breaking time symmetry. And the motion theory angle just helps clarify why it feels so fundamental. The universe is like structured motion, keeping this incredibly precise phase ledger. If the underlying rhythm is invariant under some change, the ledger entry for the corresponding conserved current cannot be altered without breaking that invariance.
So maybe a way to put it is, symmetry is the universe saying, I don't care about this change.
And conservation is its promise. Okay, because I don't care about that, I promise to keep this constant.
Or maybe every conservation law is like a receipt, proof that invariance was paid for.
I like that. A receipt paid in advance by symmetry. Ultimately, it was always about motion. Noether just wrote down the rules of its memory.
So, as you, our listeners, look around maybe at water flowing or light catching dust motes or just the stability of the world, think about the hidden symmetries. What invariances, what rhythms might be silently enforcing the conservation laws that make your everyday experience possible? And how might things change, subtly or dramatically, if one of those symmetries were to bend or even break?